on it, and we get a document. And then that document is composed of tokens. And then if we print out like all the tokens text for each token document, we get the output. And you can specify like different types of tokenization, right, and so on. And the tokenization method that OpenAI uses is by parent coding BPE. And the library that they use to do it is called tick token. It's open source. And so you can like look up OpenAI tick token for yourself on GitHub and try it out. And like, for example, you know, the middle screen, like import tick token, shows you like if you take a particular text, in this case, hello community, what it'll tokenize as, right? And these are actually numbers essentially corresponding to the IDs of each of the tokens. So you can arbitrarily like assign an ID, a numerical ID per token, right? I could say something like hi has like ID 1, and then like dog has index 2, and so ID 2, and so on, right? Up to all the tokens in level type. And you can see that here, right? Hello community is 3 tokens, and token IDs are 15,496, and so on. Okay, so we've tokenized our data into like tokens, right? So these much smaller representations of the text. But we still need to represent these tokens as vectors, right? As numerical data to feed into machine learning models. So how do we do that? We do it through what are called embeddings. And embedding is essentially just a vector that represents a word, right? So if you're familiar with linear algebra, you know about vectors. If you're not, just think of it as like an array of like floating point numbers. And there's 2 types of embeddings. One is called static embeddings, where you just give each token an embedding. And another is called contextual embeddings, where you have to like take an entire sentence and you'll give each token within the sentence a different embedding based on its like semantic representation within that sentence. And we'll see exactly what that means very shortly. So essentially you get the text, right? The input text, you run it through tokenization, and then you run it through what's called an encoder that'll give you what's called a context vector, right? And this is the embedding. And then that context vector will go through what's called a decoder and get you a list of probabilities of like all the output tokens. And then you can convert that into contextual representation of the summary. Okay, so it's really important to understand static embeddings. If you understand static embeddings, then contextual embeddings will follow pretty naturally. So the idea is this: we think about text as, you know, like strings, right? But another way to think about text is actually as vectors. In particular, there are like mathematical relationships between words. So like, for example, if I take like the vector, you know how in math you can add 2 vectors and subtract 2 vectors. In the same way, we can like convert the words king, queen, man, and women into vectors. And we can essentially use mathematical operations on them, right? So for example, what is king like minus man plus woman, you'll get queen, right? So like essentially, if you convert the words or tokens into vectors, and then like they'll have these like geometrical, essentially semantic meanings between them that like essentially represent the relationships between words. And exactly what the vectors are is somewhat arbitrary, but like essentially, as an example, like dog might be like a list like 0.92, 0.28, and so on. And by the way, word2vec, I guess I can go back. Okay, word2vec is a paper that explored this a while ago. Stands for essentially word to vector, and so it like used the method to convert words into vectors. And if you're interested, that's a really good paper to check out. It kind of like influenced the view of the ML community today, which essentially like now it's very like standardized to view words as vectors. So what's cool about vectors is that we can measure the similarity between vectors really easily. So essentially, if I have 2 vectors, right? Like let's say I have a vector like this and a vector like that. If I want to measure the similarity between the 2 vectors, I just essentially want to measure the angle in between. So if the vectors are like this, if they're pointing in the same direction, they're very similar. And if they're pointing like away from each other, then they're like quite separate, right? Very dissimilar. And so how do I measure the angle in between? I can use what's called cosine similarity, which is where like if the angle in between is 0, right, then the cosine of 0 is 1. And if the angle in between is like 90 degrees and the cosine of 90 degrees is 0. And so there's a mathematical property where if you take the cosine of the angle in between two vectors, it's equal to their dot products, dot product divided by the product of magnitudes. So you might remember this from Calc 3 or a similar class. And essentially, the idea is we want to normalize the dot product into some value between, it should, I think, say -1 and 1 instead of 0 and 1. But between -1 and 1, representing how similar the two vectors are. So here in this example, there's a small angle in between the vectors France and Italy, because France and Italy are like very similar concepts of both countries. Whereas like ball and crocodile will have a farther angle in between them because they're not as similar of a concept. So mathematically, if you're to calculate this, the dot product is just where you take two vectors and you go through each element within the two vectors and multiply them and then add the result, right? So you put the vectors together and then you multiply like across, right? 2 times 8, 7 times 2, and then 1 times 8, and you add the result, you get 38. And we want to normalize it. We want the score to be something between -1 and 1. So we'll divide by their magnitudes. So what is the magnitude of the vector? It's the square root of the square sum of its the squares of its elements. For example, the magnitude of the vector 2, 7, 1 is square root of 54. Right? If we divide by both the magnitudes, then we get the angle, the cosine of the angle in between, which is about 0.45 in this example. Okay, so static embeddings work pretty well. To some extent, in that they like capture relationships between things. But they do have some problems. So this is really illustrated if you'd like take examples of sentences. So here's two example sentences. The first is, I will wire you $1,000 from my bank account. And the second is, he was so wired, he paced the riverbank for an hour. Now, in these two sentences, we see the word wire and bank in both sentences, but they mean different things in the respective sentence. And the problem with static embeddings is that they essentially just assign one embedding vector per word. And words have many meanings. And so like that vector is not going to generalize very well across sentences. So here, right, and in the first sentence, wire is a financial wiring, bank is a financial bank. And the second, wire is more of like a mental state, and bank is a riverbank. And so even though these are the same words, they have different meanings. And so if we really want to understand what a word means, right, we need to evaluate the sentence in which it's contained in. And this is the idea of contextual embeddings, right? The idea that language is context dependent. You can't just naively assign one vector to each word. You want to give it a different vector depending on how it's used within a sentence. So we get what's called contextual embeddings, right? We don't want to view words in isolation. We want to use the entire sentence as context for a word. And large language models are going to use contextual embeddings. You essentially like have a static embedding at like the very first layer of the neural network, and it's going to transform it into contextual embeddings through what's called the transformer. Okay, so if we zoom out into the back into the language model, we see that we have a textual input, and we generate a textual output. We can also generate this lower right corner, which is the embeddings. Right? So this numeric representation of text is literally just the vector representing the input, or some transformation. Okay, so now that we know that, how are these models trained? They're trained typically in 3 stages. The first is called self-supervised learning. The second is called instruction tuning. And the third is called reinforcement learning from human feedback, or RLHF third order. The bulk of training is through the first stage, self-supervised learning. And so the idea of this is that you collect a data set of a gigantic size that you call a corpus, right? So you essentially scrape terabytes, or in OpenAI's case, like a petabyte of data from the internet. And what you do is you pre-process this data into prediction pairs. Right? So, for example, you can take either the red pill is the input, and then or is the output. So essentially, the way machine learning models work is that you give an input and you expect to predict an output. And in this case, we're giving it the input training data. You can either take the red pill and then the target output is OR. And you can see how you can like generate a huge amount of data this way, because like any sentence you can split like a ton of ways, right? You can either take the red pill or and is the input in the second case, and then the is the output word, and so on. So like for a single sentence, if you have like 10 words, then you can generate like 9 or 10 possibilities for like the pairs, right? For the inputs to the outputs. And this is called self-supervised learning because in traditional machine learning, a human has to go in and take all the training data and annotate it by hand. But in this case, the structure of the data is inherent. And so like sentences go from like left to right. And so like just by having the text itself, you can essentially split into prediction pairs without a human annotating anything. And so we call it self-supervised. So if you do this at a huge scale, if you do this on terabytes and terabytes of data, and you spend like $10 million to train on 10,000 GPUs, what is the result? You do get like a model that models language really, really well, and has a good understanding of grammar. But do you get ChatGPT? And the answer is no, because if you give it at this stage, if you only do self-supervised learning, then if you give it the text like what is the capital of Italy, then it might generate something like what is the capital of France, what is the capital of Spain. What's it doing? What it's doing is it's copying essentially the traits of its training data. So what might happen is that it might have trained on like a quiz of like what is the and on that quiz there might be questions like what is the capital of Italy, what is the capital of France, and so on. And if that's the case, it's just going to copy essentially the distribution of the training data, and it's not giving you an answer. And that's not what we want. As a human, we don't want to just like copy data from the internet. We want the answer. So to get an answer, we need what's called instruction training. That is, we need to tune the model to follow our instructions. So essentially what's happened is that like there's a ton of training data, and it seemed like a lot of different representations of the training data. So for example, like if you ask the large language model for test advice, it has like multiple personalities, right? It's had like, it's seen a ton of training data on tests from across a ton of different people, and essentially has a ton of different like perspectives on tests. And so like you have like a genius like Magnus Carlsen like test advice, and you also have like the Reddit response that gives you like technique. And so like there's a bunch of different like training data on the internet. Some of it is good and some of it is bad. We want to elicit the former response. We want to elicit the most helpful response possible. And we need instruction training to do that. So what happens is essentially a human needs to go in and collect a data set that is being annotated. In this case, like there's a bunch of different tasks, right? One is like common sense reasoning, which means like you give it, you know, an input and you give it a list of options for what to do. In this case, like if you want, like the input is get a cool sleep on summer days, and the options the model can choose are like keep a stack of pillows in the fridge or keep a stack of pillows in the oven, and like the correct response is to put in the fridge to the spot. And then the next task is translation, where you translate between English and Spanish, and so on. So there's a bunch of different tasks in machine learning and natural language processing that we can run through. And this is what we call instruction training. We essentially fine tune on a whole bunch of different tasks. And then like when you get a new task, it essentially like will do pretty well because it's like essentially understood not only the meaning of language itself, but also how to generalize to a number of different. The final stage of training is called reinforcement learning from human feedback. So this is actually like pretty technically involved. If you are familiar with reinforcement learning, it's essentially where like you, it's a like type of machine learning where the model like can interact with its environment. So like the model is placed in the environment and it can make some actions that influence its environment. For example, like if it plays playing Go is an example of reinforcement learning, because the machine learning model can choose like moves to make on the Go board, and then after that, its opponent will move, and it'll have a new environment, like this is a new state of Go board for you next. And that's what we call reinforcement learning. RLHF is an application of reinforcement learning to large language models. And in particular, the idea is you take like a set of responses from the large language model. So large language model can generate multiple different responses. And so you essentially like collect, like, for example, 4 different responses in the model, and you have a human rank them in order of best to worst. Right? So you can see that in step 2. You can see like it generates 4 different responses, A, B, C, and D. And a human is going to label the data, ranking the responses. B is better than C, which is better than A, which is better than B in this case. And the model will use reinforcement learning through a state-of-the-art algorithm called proximal policy optimization, or PPO, to train the reinforcement learning, like reward model. So the intuition behind this is that as a human, it's oftentimes easier to evaluate which responses are better or worse rather than write responses yourself. So for example, if I ask you to like write a haiku about machine learning, it might be very hard for you to do that, but it's much easier for you to like evaluate 4 different responses of like write a haiku about machine learning. It's pretty easy to rank responses in the machine learning model from best to worst. Like it's easier to tell what makes what is a good haiku than to like write a haiku. And the other aspect of this is that OpenAI has like a lot of obligations to make their large language models safe. And so like oftentimes, you know, if you ask it like something bad, it'll say like, hey, like I can't do that. As a large language model, you know, I can't like give you advice on how to assassinate the president or something like that. And how you do that, to make this model, to make the model say that, you use reinforcement learning from human feedback. You essentially what we call align the model to human safety. And there's a little bit of an aside of like why we want to use reinforcement learning at all, because reinforcement learning is traditionally for like video games and other kind of environments. And the reason is essentially like typically when we train these large language models, they essentially exhibit like a distribution, a probability distribution over text. And instead of like creating this distribution, we want to elicit like the responses that are safe and helpful to humans. And that's exactly what reinforcement learning does. Reinforcement learning is what's called mode seeking, which means like it'll essentially exploit like the highest probability ones. And so here's like an illustration of what ChatGPT looks like under the hood. Essentially, if you just train using unsupervised or what we call self-supervised learning, then you have this like monster that like models language, right? And so it knows like everything about language. It like knows a huge amount of like human knowledge. But if you just ask it stuff, like there's a lot of danger, there's a lot of misinformation, and so on. And so we use supervised fine tuning, right, or instruction tuning to get a much nicer model. And then to get it even better, we use reinforcement learning from human feedback. And that's why, like, when you use like ChatGPT, it's not like this mean, cruel thing that it can like that like gives you hate speech. Instead, it's like this nice little bot that is like essentially like has endless patience and is always very happy. So it's really important that we do supervised fine tuning and reinforcement learning from human feedback to get the models up. And finally, we have what are called emergent abilities as we train larger and larger models. So the reason they're called large language models is because they're language models that are literally like extremely large. Well, and what we mean by large is that machine learning models have what are called parameters. And the more parameters you have, essentially like the larger the model is, like the more RAM it takes. In this case, VRAM, which is like RAM on a graphics card or GPU. But essentially, like it takes up more and more space, right? And it's like it takes up more and more compute to run, the larger it is. And what we've seen is that as we train larger and larger models on more and more data, we actually end up getting abilities that we didn't like explicitly program into the model and that we didn't even expect at all. So for example, like to write poems that rhyme, this is like a really strange thing because like the model can't like hear, right? In an auditory sense that humans can. And so you wouldn't expect it to write poems that rhyme. But if you like ask ChatGPT, it can write poems that rhyme. And this seems to be some kind of emergent ability from just having seen so much data, right? That it seems to have some kind of understanding of what rhyming means. Or to translate between languages. Like ChatGPT can translate between major languages, even though it wasn't like necessarily specifically trained to do that. And to write code that compiles, right? We didn't like make a model that like intentionally will like just output code, but it happens that by modeling like so much data, it's actually able to write code that compiles really well. And these are emergent abilities because they happen in the latest versions of ChatGPT, like 3.5 and 4, but they didn't work so well for ChatGPT, for GPT-2 and earlier, which were like very early versions of GPT. So they found that like as you make larger and larger models, essentially has more, they have more and more abilities they wouldn't necessarily expect this. So this is an example from like when ChatGPT was first launched. You can't do this anymore, by the way. It'll say like, I am a chatbot, not a Linux terminal, because like they use like reinforcement learning from human feedback to like not let you do this for security reasons. But way back when, someone like just played around with ChatGPT and said, hey, like you're my Linux terminal. So my first command is print the working directory, and it literally like acts as a Linux terminal. And what's happening is that it's not a Linux terminal. There is no Linux terminal, but ChatGPT is like believing it's a Linux terminal. And when you say like, you know, echo print hello world into test.py, it creates a new file, right? With the contents test.print hello world. And then when you execute it, it's like pretending, it's like hallucinating that it executed it, which is like really cool. So like there's nothing actually being executed here. This is like 3 code interpreter and everything else. ChatGPT is literally like believing that it executed the code, right? And acting as a Linux terminal just because you told it to. And this is an emergent ability that we didn't really expect, but that's like happened to work because the model is so much. Okay, so to recap, we went through 5 things today. The first is tokenization. How do we convert like some gigantic amount of text into smaller units called tokens? We talked about different levels of tokenization, character level, word level, and subword level tokenization. Subword level, which is the most commonly used today for its effectiveness. Second, we talked about embeddings, which are essentially vectors that represent tokens. So we talked about the idea that like vectors can represent like relationships between tokens, and also how the difference between static embeddings and contextual embeddings. Where static embeddings like assign a vector statically to every token, whereas contextual embeddings take into account like the entire context of the sentence and are able to discern between multiple definitions of the word. Third, we talked about instruction tuning, which is where we like take a model that's been trained right through self-supervised learning and convert it into a helpful agent to help us right follow instructions. Fourth, we talked about reinforcement learning from human feedback, which is where we use reinforcement learning to essentially further elicit the responses that are helpful and safe to business. And finally, we talked about emergent abilities, which are abilities that we didn't expect the model to be able to perform, that we didn't explicitly train on, but that the model exhibits when it is so large and has seen so much data, been trained for so long on so much data. So that's in my further presentation. If you want to get in touch, best way is to send me a message on Twitter. I noticed that Twitter is also like essentially where a lot of the machine learning community is. So you can follow like a ton of people that, for example, like work at OpenAI, like Sam Altman and Elias Skever, who's a chief research scientist, and so on. And there's like a lot of scientists other scientists on Twitter as well. So I highly recommend you check that out. So thanks, Sebastian. Thank you guys.
Okay, so hey everyone. For anyone who just got in and noticed that there's not any Chick-fil-A here, we had a bit of a communication breakdown with SG, but but we did order some pizza that's gonna be here in about 20 minutes, so don't run just yet if you're hungry. And you already saw Angel left and he'll be back with that soon.
Okay, so apologies for that miscommunication, also for the miscommunication about theory of transformers, but that's probably more better suited for what we're gonna be talking about today, and for the for the purpose of AI applications, understanding this is probably more important than the theory behind the transformer model. Okay, so what I'm running here is a notebook that I just shared on the announcements for SSD. And what I'm going to be talking about here is, well, sorry, that was actually the wrong Jupyter notebook. Be running this. Okay, so to get started, I will be going over the hosted inference and how basically the ecosystem is organized at the moment. We have the infrastructure services at the very, well, here like visually at the very top, but really it's like the lowest level, because these the infrastructure is where the models are running. This can include any of your any cloud provider, for example, Azure, AWS, GCP. And I also added Hugging Face because I'm not really sure where and how they run their inference, but it could be Azure, it could be a cloud provider, it could be themselves. Underneath the infrastructure, you have the AI research, which well, this isn't AI research isn't necessarily a service, but the reason I put it in there is because these AI research labs or organizations, they oftentimes have their own service, their own API service that you can reach out to, and they're gonna receive a much more simple query from you, parse it, and then actually query the model that is running on the infrastructure. So AI research should really be like AI research and then parentheses API layer where clients interact with. Underneath that, you have proxies. So just, I was a little unsure about whether to put clients inside proxies, but I left it in there. So a proxy is basically any service that just reroutes whatever you send to it to another service. And a very clear example of this is Brain Trust, which is the B symbol in black. And what they do and why you would want to use them is because, well, one, it gives you like a single entry point to be able to interface with any of the AI research models, and by any, it's a subset of the AI models, which can be OpenAI, can be Anthropic, can be Hugging Face. And what do they provide outside of being that single entry point? They also provide something that is very important, particularly if you've ever tried creating ChatGPT plugins or GPTs. They provide analytics and telemetry on how the service is being used, which means if you have half your user base using OpenAI, it's gonna illustrate that. It's gonna give you the analytics. Half the user base showing Hugging Face, so it's gonna give you the analytics for that. And it also gives you other controls and other pre-processing that is abstracted within Brain Trust. So that is a hosted proxy. Then underneath that, you have clients, which are programmatic ways to basically interface with the hosted with the hosted inference providers. And the number one and the most important of these clients is the OpenAI client. The reason I say this is because OpenAI is kind of leading the dance, and as a consequence, they're leading the dance and they're doing a really good job on how their API is structured, what paths lead to what features. And all of this is open source, and all of this is very clearly documented. I can share the link later, but yeah, so that's the OpenAI client. That's what you install when you do npm install OpenAI or pip install OpenAI. And just to further like reinforce why it's so important, Light LLM is another service which is what this notebook is based on, that utilizes the same structure and the same methods and of the OpenAI client, and then returns the same outputs. That way it standardizes the way you call the different providers. And I will be getting deeper into that later, but that's just one of the many services that are incorporating the OpenAI client, quote unquote, standard. And then on the right of that, you have basically a community illustrating that anyone can access any of the models, any of the AI research endpoints, or maybe even infrastructure. Well, if you're like an enterprise customer or company, you could actually have a GPT-4 or a GPT 3.5 hosted on Azure, which means you could directly access the model. You can directly access the model being run on infrastructure. But for most of us, we're going to be accessing it at like the AI research API layer. Also, another thing I forgot to mention here. On the AI research level, you have like another community there that symbolizes actual individual independent researchers, and they can upload their models, their work on Hugging Face, and that's going to be deployed on their infrastructure. And I think it's, well, for my purposes, it has been pretty much free. So I'm not sure if at any point you have to pay to share your model, but yeah, if you're a researcher, you can do that. So here is an example of like the OpenAI client. And as you can see, it is unopinionated on which URL you're using. So for example, if you are running if you're hosting your own like API endpoint that is calling an inference, that is calling like a model, you can actually just add it here, which is what Brain Trust does. You add it here, and the API key is optional. That is if you care about authentication and about your compute resources. And then this client is actually going to call your URL as opposed to OpenAI, which is the great thing about what they're doing. So moving on to Light LLM. Again, what they do, they standardize the inputs and outputs so that you're able to access any model in the same way. So if we go ahead and import the packages, we initialize the OpenAI client, and then we set up the prompt here, which is what is the weather in Gainesville? If you ever tried this on a chat model, you probably already know what it's going to respond, but it conveys the message. So here we have side by side the Light LLM, us using the OpenAI client and us using Light LLM, which is using a Hugging Face model. And as you'll notice here, the OpenAI client is taking in the same inputs as the Light LLM completion. So that's one of the key important things. And as you see here, we get the response in the same way, through the same, it's the same JSON response that is returning, that is being parsed by the package, and then providing it to you in like a pydantic object. So if we look at the responses, we have the OpenAI response. They're going to be different. They're different models. And there's also a temperature associated with it, which I'll go to in a moment. But you see, we're able to get the responses in the same object path. So this works with other use cases beyond completions, for example, embeddings. And sometimes the Hugging Face embedding model is actually sleeping, so it doesn't actually run. Is that the case? Yes, it's currently loading, so we're going to need to give it a second. So it also runs with embeddings. It also, Light LLM also supports embeddings, just like OpenAI supports embeddings. And I think it should already be loaded by now. Let's give it a shot. Good. Okay. So now we have the embeddings. The OpenAI embedding is a vector of 1,500-ish size. Then the Light LLM embedding, which is a Hugging Face hosted embedding, is 700-ish in size. It can also do streaming, and we're actually gonna, well, I'm gonna try using the what is the weather in Gainesville prompt, and if that doesn't work, we're gonna change it because I do want to demonstrate something. Okay, so it is streaming it continuously. And that is something else that the OpenAI client supports. And I'm gonna run it again, and I'm gonna ask you guys a few questions. So if we run it again, you'll notice that it didn't really convey the same thing you'd expect from a stream. It automatically returned the generation to you. Anyone know why that's happening? Why it automatically returned the entire generation as opposed to token by token? So, okay, so the reason is it's being cached by Hugging Face, and that is one of the topics that we could cover in a later workshop on how to do effective caching. And another thing, so we know that it's being cached, but how was it cached? Like, how is it returning the response? Is it returning the response as a single generation, or is it still returning the response as multiple tokens, but just instantly? Any ideas? Honestly, if you haven't worked with this, you might as well just shout a guess, because there's no way for you. Throw a guess. What was it? Yeah. Exactly. That is the right guess. So it's basically returning token by token. The way it is cached is it is caching the individual token responses and returning that. For example, as opposed to ending it with without any new line, if we force it to end with a new line, you can see that it's still returning chunks by token. Okay, so that is streaming. And then here's one really cool thing, and one of the potential use cases of a package like LLM. So for some background, OpenAI has this model that was trained to follow instructions. It was trained to respond to you in a JSON format according to a JSON signature. And the JSON signature in this case is illustrated here. What this model is called is function calling. And the purpose of it is predictable outputs from the LLM. And this is something that only a subset of OpenAI models, and apparently Claude supports it as well. Only those few small subset of models actually support this. And definitely Mixtral does not support this. And as you can see here, I'm using the model Mixtral, yet I'm still passing it functions. So you would expect, you wouldn't expect this to work, but what LightLM does is, and I'll run it in the meantime, what LightLM does is it imposes a prompt in addition to your prompt that tells it to, and in fact, I actually have this link here, that tells it to, hey, here's your function signature, and please return an output in a JSON format according to our function signature. And if we open this, this is actually what's happening behind the scenes in their code base. Give a second. Okay, so this is what it's doing. Whenever you call a function call in a model that doesn't support it, it just adds this to the prompt. Produce JSON output only. The following functions are available to you, and it adds a function there. So that is what LightLM is doing, making it so that other models have the same functionality as other models, which they shouldn't have. Sorry, I probably botched the communication of that one, but I hope that conveys the idea. And then if we look at the response, well, I basically do, here's a thing of note. I do need to modify the returned response for Mixtral, because it actually doesn't return a parsable JSON output. I don't know why it does that, but if you just if you do some parsing of its output, you can get it to a point where it's actually JSON parsable. And that's what I end up doing here. I do JSON.loads and then JSON dumps of the generated response, and it returns the desired response here. So this is what I was hoping for. JSON content functions, the name of the function signature, and then the parameters that I asked for in the signature. And that is something I didn't exactly cover, but this function signature is very similar to an open API specification, if any of you are familiar with that. And what that does is it communicates how to communicate with an API. And in doing that, you tell it what are the expected inputs and what are the expected outputs from calling this API. And in this case, the expected inputs are here under properties, location of type string, the description, and then unit, type string, and then it's an enum of Celsius or Fahrenheit. Yeah. So that is light LLM. Oh, and here's an example of doing the same there's an example of calling the same exact call, just to a different model. This model is Falcon 7B. It at one point was like the state of the art, was a really good model, but it's kind of fallen by the wayside now. And as you can see, there's an error whenever we actually parse it, and that's because this is well, okay, in this case, it's actually loading, but if we run it while it's actually loaded, then it's still breaks. All right, it's still loading. Hopefully it's unloading this time. Okay. Maybe we'll get back to it later, but what I was hoping to illustrate here is that prompt engineering isn't very reliable. So fine-tuning models is probably the best approach. But if that is not feasible for whatever your situation or use case is and whatever your resources are, then prompt engineering is your second best option. All right, so any questions on using hosted inference? Okay, so moving forward to hosting models locally. If you are like a data scientist and you're very familiar with the architectures that you're going to be working with, the architectures of the models, and you plan on actually modifying the architecture or doing some changes, training, whatever, you should probably use some sort of framework like PyTorch, JAX, or Python, sorry, and TensorFlow. But in this case, since we're looking at things that from a higher level, we're only going to be using Hugging Face. Which is a pretty neat, neat organization that offers packages like the Transformers library, which allows you to, which takes care of allocating the weights of the model and basically running the model provided with a much higher degree of simplicity. So in this case, the model that we're going to be using is Mistral 7B version 0.1. And this is actually just a causal model. It is not it is not instruction tuned to behave like a chatbot. So that's just a disclaimer as we move forward, but we're going to be using the instruction model later on. So if we load that model, I already downloaded, so it's a lot faster on my computer. Oh, well, another thing, this is actually running a hypergator, so it's not necessarily my computer. My computer wouldn't have a chance at actually running this. You need at least like 13, well, around 12 gigabytes of RAM to actually run inference of a 7 billion parameter model. As loading it itself consumes 7 gigabytes, and then running inference, it's an additional necessity in VRAM allocation. So we load the model, and then before we continue with like how to actually like control the model's outputs, I'm just gonna do a warm up. Well, I'm gonna discuss what the model is actually returning. So when you run the model, let's say hypothetically you have a model with a vocabulary of you will, win, lose, and you pass in the input you will, then the model will output well, first you pass in the input, you will. The model will first output a series of logits that are unnormalized. You normalize those logits, and then you return. So and then you'll have something like this array here, where it's a probability distribution, showcasing that U has a 10% probability of being selected, then will 10%, win 50%, and lose 3%. And then from there on, we can make an informed decision on which token to select. And arguments that take advantage of that distribution of that probability distribution are top K and top P. What top K does is it selects from the top from the highest probability tokens. So for example, if your top K is 2, it's going to select either win or lose after you pass in the input you will. Then for top P, it's going to select anything over the P that you indicate. And what the P is a probability. So for example, if we set P to 15%, 0.15, it's going to return only win lose. And then temperature, it just randomizes. It uses the probability distribution to select which to select a token. So if we only have the win lose tokens left, then it's going to have it's going to select between one of those two tokens depending on their probabilities. And a higher temperature is going to result in more randomness, whereas a lower temperature is going to result in less randomness. So it's more likely to select the highest probability. Okay, so moving forward with actually generating from the Mistral 7B model, we're going to use this pipeline method from Hugging Face, which is as simple as it gets to use one of these models. And again, here's to reiterate, this is the function behind the temperature, how temperature affects the probabilities. Probably should have moved this cell up one, but the modified probability is equal to the initial probability to the exponent of 1 over temperature. So if we have a very low temperature of like 0.01, then it's going to be P, or if we make it 0.1, it's going to be P to the power of 10. So that means that any tokens with a probability like close to 1 aren't going to change that much, whereas tokens that are further from 1, like 0.1, are going to dramatically decrease. And that's what you see here in the graph below. Whereas if you do a temperature of 0.1, then the difference between like the highest probability token and then the second, third, fourth is a lot greater. Whereas if you set the temperature to 0.9, which is basically the modified probability is the same as the original probability, it's not going to change a whole lot. The difference between the token probability is very similar. So now we're actually going to run the generation, and in this generation, it's kind of more catered towards a causal generation, which is just predicting the next token. And what we're predicting here is what is the future? Well, I'm prompting the future of AI is, and it's just going to continue from there. So the generated text is bright, and it's only going to get brighter, blah blah blah. Now, if we move on to an actual instruct model, there we have the ability to actually have a conversation with the model in like a message by message format. How we do that is we format the prompt to follow a very specific prompt structure. And that is something that Jim already touched on, which is in the case of Mistral, this is what it looks like. You have the start of sentence, then you have an inst indicating like the beginning of a message, and then another inst indicating like the end of that message. And then eventually you're gonna the model is gonna generate something here, and it's gonna finish things off with an end of sentence like this. So you can pass in the prompt as a string, or you can use a plug and paste method that does that for you for prompts that where this is supported. Mistral is one of those, sorry, for models. I think I said prompts. For models where it is supported. And Hugging Face provides this apply chat template, which is gonna add your prompt to the chat template. And this is kind of like a trivial method, but when you consider how sensitive the model is to following that template, then it kind of justifies its value. It justifies its existence. So if we go ahead and run this, we have the initial prompt, which looks like this. And then it's going to return the initial prompt plus the generation, which is as opposed to what we saw before, where it was saying where the generation was write, comma, dot, 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 not like an actual conversation. Here it's actually restating what I asked it to. Well, I don't know if you can even categorize that as a question, but it's restating what I said and then answering it. So the future of AI, artificial intelligence, is the topic of much debate, blah, blah, blah. So it's actually following that message format. Then, what is this? Okay, so this is the original. Sorry, let me break this. Okay, what this is, the prompt that I'm passing in this generation is the future of AI is without the prompt structure for a without the conversational prompt structure. And as a result, the model is just going to continue the generation. So even though it's an instruct model, it is not going to follow the conversational behavior if we don't pass in the conversational prompt structure. And that's what this is illustrating here. The generator response is, well, remember that it's passing in the original prompt, and then, well, this is the original prompt, and then it's continuing with not just about making machines smarter. So it's not really having that conversational generation that we're expecting. And here's another demonstration of why you need to be really careful about using the conversational prompt structure, because like if I run this, here's the original prompt, and we generate from this, it's also going to fail. The future of AI is, and it responds with a topic of great interest. It's not restating the prompt, which is what we're expecting it to do as a conversational model. Any idea why it didn't work? It has to do with the prompt here. All right, don't worry about it. You guys are on the same boat as a senior machine learning engineer at AWS, well, at Amazon. These two spaces basically broke the model. Because of these two spaces, the model didn't recognize that we were asking, like, we were expecting a conversational response from it. And as a consequence, it's literally just continuing. The future of AI is a topic of great interest. So that's why we need to be really careful about following this this conversational structure. And if there's any doubt, like, never mind, I won't get into this one, but yeah, so that's how we can use like the pipeline to that's how we can use the pipeline to generate responses. Now I'm going to get into a more granular usage of the model, where we have direct access of the model's response logics. So again, so far, we don't have a lot of control over how the model generates its response. Using pipeline, we only have access to the top K, top P, and whatever other arguments, including the temperature. And from that, we get a complete generated response. So if we want more control over how it's selecting the next token, or we want or we want to, like, for example, stop the generation at an arbitrary point, then we're gonna need more granular control, and we're gonna need an autoregressive generation of the model. So first thing we're gonna do is we're gonna import the packages. Then we're going to initialize we're gonna be using the GPU device with the CUDA architecture. Then we're gonna be using the Mistral 7B instruct model. We instantiate that model as auto model for causal LM, which stands for language model, causal language model. And then we set up the tokenizer. We run this, and that's just gonna load the model again. So a key part of this is thinking back about the logic. Thinking back to the logics. When we're, and I guess I'll go into like the specific code. So in the input, we're gonna get the input, a prompt, right? The usual. And then we're gonna tokenize that input. These are the steps that, well, let me begin by saying these are the steps that you're gonna need to follow to generate, to have the LLM generate a token for you. So first, what you're gonna need to do is you're gonna get the input text, which is a string. Then we're gonna tokenize that string. Then we're gonna get, well, this is like a Hugging Face specific thing, but we're gonna get the input IDs, which represent just the actual token indices that each string represents. Then we're gonna run torch nograd so that the model is not modified when we run inference on it. And then we're actually gonna throw the input IDs into the model, and it's gonna generate output logits accordingly. So if we run this, this is what we get. So loss is something that you would, the reason loss is none is because of torch nograd. And additionally, the logits returned are a tensor of the following shape. And this is what the logits look like. These are the unnormalized logits. And this is the shape of the output logits. One indicating the current batch, 6 indicating the tokens, and 32,000 indicating the vocabulary size, because it's returning a probability for every single token in the vocabulary. Any idea why it's returning 6 probability distributions? Like why it's giving me the probability distributions for each one of the tokens? And I'm kind of gonna throw this to Jim as well. I actually don't know. Does anybody know? Why are we getting the probability distributions for each one of the tokens when we're using the model for generation? So I'm running the model through Hugging Face, and whenever I pass in the tokens, it generates the output logits. Here's the input text. I tokenize it. I throw it into the model. And then what it returns is the output logits, which is of shape 1, which is a batch. 6 is the output logits for each token, and 32,000 is the vocabulary size. You can fill us in with this later, but for now, we're only going to be focusing on the very last probability distribution, which is what we're looking for to predict the next token. So now that we have the output logits, we are going to use those output logits to do this really strange like filter on those logits. And feel free to walk out now, because what I'm about to like show you is like complete garbage, but it is an idea that I wanted to experiment with. So to, okay, this is something that we're gonna get to later. We're just gonna move over to the hypothetical filtration system for the logics. And what that looks like at a high level, I'm not gonna run through the code because it's a little extensive, but what it does that at a high level is first, the user is gonna provide the original prompt. Then the user is going to create a prompt for semantic comparison. And the use case of this would be, you can either create a prompt that says, hey, answer, give me an answer. So that, okay, respond in a way so that it imitates like Elizabethan English, which is like the way that Shakespeare writes. So write in a way, write in Elizabethan English. And you can add that to your prompt. And that's adding extra tokens that are going to need to run through the model. And that you're going to need to run that every single time a user uses your platform. So that's like one option that you have. Alternatively, I'm proposing this option, which is you pass in a prompt for semantic comparison. And what I'm proposing here is that you pass in like Shakespeare as the prompt for semantic comparison. And from that prompt, it's going to, we're going to embed that prompt, and then we're going to embed every single one of the tokens. And then we're basically going to get the cosine similarity between each one of the tokens and the original Shakespeare prompt, which means that the tokens that Shakespeare would use, like thou art, thy, those words are going to get elevated in probability, whereas other words are going to decrease in probability. And I imagine that this could lead to a lot of problems, but that's something for me to worry about in the future. So yeah, we do the cosine similarity between the tokens and the embedding comparison prompt. And that's how that side of the input is running. On the left side, we have the create prompts. We tokenize the input. We run it through the model. We normalize the logics. And then at the very end, we just multiply the logics output by the multiplication of by the cosine similarity of the semantic comparison prompt and the embeddings of the tokens. So what that gives us is something like this. And in this use case, to narrow down the scope, I'm using there's the input text. There's, okay. I would be surprised if this actually worked. So I do not. Did I ever? All right, we'll see. We'll navigate the error. Okay, yeah. So this is generating. This is first we're gonna. I'm gonna show you the actual use case that I'm using here, which is this is the original prompt. Select the university of your choice within the southeast portion of the US. Only respond with the name and nothing else. So university of underscore. And then if we run that through the normal pipeline without this strange filtering, we're going to get this as the response. University of North Carolina at Chapel Hill. That is not exactly what we want. Now, if we add the semantic comparison prompt of University of Florida, and we run the same pipeline, and you can inspect this for yourself. I'm not doing anything that's I'm not doing anything shady here. You can verify that yourself. And if I am, hell, congratulations, you can submit. But it actually outputs University of Florida instead. So there's a way that you can like kind of coerce the model to do what you want. And I did take one shortcut that I'll admit, and that's out of laziness and kind of like fear of it actually not working, which is I'm only getting like the top. Let's see. I'm getting the top. I'm getting the top 10 tokens from the probability distribution. And I'm only embedding those top 10 tokens, and from those top 10 tokens, I'm actually running the whole system that I illustrated before. And the reason I'm doing that is because I don't want to run the embedding through 32,000 tokens. But if you're actually building this as a, I don't know, as an app that you want to deploy in your company and it's going to receive a million uses for like whatever, it could actually justify the initial cost. So yeah, this is just an experiment that illustrates how you can control the output of a model. How you can control the output of a model in a token by token basis. And it's already 7:38, so I'm gonna stop here, but there's also another notebook here for evaluations, which I could touch on later. But yeah, this is it for today's workshop. Yeah. I'm gonna be adding to the announcements in SSD a survey to see what you guys think and get some feedback. I would really like to hear like what tools you guys would like us to cover and perhaps what areas of the AI application pipeline you guys would want us to focus on. So really appreciate you guys being here.